Hello everyone, in this video I will talk about moisture content of wood. Moisture content is very important for wood specimens because their physical properties and mechanical properties such as weight, shrinkage, and strength, all of them depend on the moisture content of wood. The moisture content of a wood specimen is defined as the weight of water in the specimen expressed as a percentage of the oven-dry weight of the wood. An oven-dried wood sample is a sample that has been dried in an oven at 100 degrees Celsius to 105 degrees Celsius until the specimen attains a constant weight. Moisture exists in wood as either bound water or free water. Bound water is held within the cell wall by absorption forces, and free water is the water in the cell cavities. There is a very important concept which is called fiber saturation point, which we often call it FSP. It's a critical level of saturation at which the cell walls are completely saturated, but no free water exists in the cell cavities. FSP varies from species to species, and it's different even within one species, but it's typically in the range from 21% to 32%. In engineering calculations, if you don't know the value of FSP or it's not provided to you, we commonly assume FSP is equal to 30%. FSP is very important for wood specimens because when the moisture content of a wood specimen is below FSP, then adding moisture or removing moisture will have a significant effect on practically all the physical and mechanical properties of the wood specimen. However, when the moisture content is above FSP, the properties are independent of moisture content. When the moisture content of wood is above FSP, the wood is dimensionally stable, so it doesn't shrink or swell with the changes of moisture. And this stable dimension, we call it grain dimension. However, when the moisture content is below FSP, moisture fluctuations can lead to significant dimensional changes. Shrinkage is caused by loss of moisture from the cell walls. When the sample is below FSP, compaction of molecular structures and the formation of additional hydrogen bonding can produce a shrinkage. On the other hand, swelling can be caused by gain of moisture in the cell walls. And this figure shows the dimension changes in wood specimens, and so this y-axis is the shrinkage and this x-axis is the moisture content. So you can see when the moisture content above FSP, there is almost no change in dimension. However, when the moisture content is below FSP, you can see significant change in the three directions. So actually the changes vary from one direction to another. So the dimensional change in radial direction are generally about 1/2 of the change in tangential direction. And the change in longitudinal direction is the minimum. Typically, when the moisture content change from 0, which is oven dry, to FSP, the change in longitudinal direction is only about 0.1% to 0.2%. So we can see that the change in tangential direction is larger than the change in radial direction, and the change in radial direction is larger than the change in longitudinal direction. And the change in radial direction is almost just 1/2 of the change in tangential direction. Also, you need to pay attention here. So this y-axis is the value of shrinkage, and it's expressed as the percentage of green dimension. So we need to use this when we solve the sample problem.